Welcome back to the final part of the lecture on natural language processing of the course on big ideas in artificial intelligence. Now, we have learned a lot in this lecture so far. We have learned about how to use these statistical patterns that manifest themselves as the context in which individual words appear in order to induce or automatically capture the meaning of individual words. And also, we use the same idea just in the other way around in order to learn in order to capture the meaning of the entire text that consists of multiple individual words. And then one can, in fact, call the methodologies or the set of algorithms that we have discussed today or in this lecture as statistical natural language processing. And that is because we rely heavily on statistical patterns of existing data that is a set of text into automatically inducing or the extracting meanings. The statistical natural language processing, despite what you have felt, because I've been using the term modern algorithms or the modern artificial intelligence over and over throughout this lecture, it might seem like it's a very reason idea. However, this is not reason at all. In fact, the history of statistical natural language processing go all the way back to 1948, when Claude Shannon, the father of information theory, indeed wrote a paper proposing the whole framework of information theory. This was immediately followed by Warren Weaver on his memorandum titled Translation in 1949. Yes, the Weaver here is what the building in which Quran Institute is located was named after. And a year after, Claude Shannon, the very same Shannon, wrote a paper on how to predict the entropy of the printed English. That is, what is the right way to estimate the distribution over English, that is the language, using statistical method. And in the same year, Alan Turing, yes, you must have heard of his name. He's the father of modern computer science, and he proposed perhaps one of the most widely discussed or the debated test called Turing test or the imitation game. And then in the paper where he proposed imitation game titled Computing Machinery and Intelligence, he actually does talk about the importance of making an intelligent system that handles language or has an ability to communicate ideas with other intelligent entities. Now, of course, it's taken many decades until these ideas started to look more real than simply some discussion on papers. In 1986, in a seminal paper by Romanholt, Hinton, and Williams, where they proposed a backpropagation, one of the examples they used in the paper was to induce some kind of vector representation of the words, or in fact, the members of family in the particular example. In the same year, or in the following couple of years, Brown et al. From back then IBM came up with the idea to use a statistical approach to solving the problem of language translation, which has become one of the foundational work on which all the recent modern approaches to natural language processing have been built. These two approaches kind of, let's say, went out of the fashion after about 1993 or 4, but then in early 2000 and early 2010s, this whole idea of using statistical machinery and also the idea of the neural network in order to build a natural language processing system was revived. And then this revival was frontiered by Colbert and Weston et al., where they very ambitiously titled their paper as Natural Language Processing Almost from Scratch. And Tomasz Miklov in 2013 proposed the idea of word-to-vec, which we looked at in the second part of our lecture. And in 2015, not to brag myself, I was involved in using this idea of statistical natural language processing and neural network in order to build one of the very early, convincingly working natural language generation system, back then in particular for machine translation. So in some sense, the history of natural language processing so far could be summarized perhaps a bit obnoxiously, as the success of statistical natural language processing, where the emphasis is on statistics. Before I wrap up this lecture, I'd like to point out one fundamental issue of statistical natural language processing in order to make sure you know that we are not at the end of the road in terms of investigating natural language processing or building artificial intelligence agent or the machine that is able to understand natural language. In fact, I want to give you an impression that we are only at the very beginning of this whole endeavor. So let's just take a very simple example. Now look at the screen. You see two symbols. You see the leaf on the top, and then you see banana on the bottom. Now you're going to see another set of symbols. Now with the same symbols, but in different colors. But what you see is that you still see a leaf on the top. You still see a banana on the bottom. Another example, blue leaf, green banana, yellow leaf, and purple, I guess this, I'm not even sure what's the name of this particular color, but then let's call it purple banana. And then what happens here is that we have changed the texture or the color of all these symbols, but we know that there are only two types of symbols, leaf and banana here. So then we can start asking ourselves, from what we have learned, that is the statistical natural language processing, where we strive to extract automatically the meaning of individual words or symbols from statistical patterns of large amount of data we have. Now, from this perspective, are leaves and bananas similar to each other? I mean, I guess the answer is quite obviously yes. Why? Because both grow from trees. What that means is that in the text, we're going to see a lot of leaves or bananas show up together, that is co-occur with words that are related to trees, forests, and whatnot. And then both of them are often edible. So a lot of the leaves are used for cooking, like the herbs and so on. And bananas are obviously almost all remaining, let's say, bananas in the world are actually quite edible. And then of course, we are going to see words such as eat, buy, cook, all these eating related words co-occur together with both leaves and bananas. So from these observations, we know that according to statistical mechanism that we have learned in this lecture, leaves and bananas are going to be considered very similar to each other. However, one thing we know, not the statistics tells us, is that the leaves and bananas are not same. They are not similar with each other because of their colors. That is, the similarity between leaves and bananas has nothing to do with the color or the texture of each of them. We don't say leaves are different from bananas because leaves are largely green, bananas are largely yellow. Doesn't make any sense. But then I got really curious. I went to Google Books Ngram Viewer and then started to searching for some of these so-called bigrams. That is two consecutive words. And then I tried to look at how often these bigrams appear in a very large corpus that was collected by Google Books. Now let's look at these two plots that show the frequency of these bigrams. On the left side, you see green leaves appear very often, yellow leaves next, red leaves next, purple leaves next, blue leaves almost never appear. And then this actually gives us a sense of the meaning of these leaves, the word leaves as well, right? Because these are the words that co-occur together with the word leaves. And then these curves tell us the frequency at which these words co-occurred across time. And then across time, it has been largely stable. Now, on the right side of this slide, we see the same thing, but instead of leaves, I use bananas in the place. An interesting thing we see is that we actually get the exactly same order of the colors when they co-occur together with the bananas. Green appears most often, together with bananas, yellow next, red, purple, and blue bananas. So blue almost never co-occur together with bananas. And by the way, the green bananas are amazing. I just put a picture that I took from Kigali, Rwanda when I visited there about 2.5 years ago. And then those are amazing. So it's unsurprising that the green bananas are mentioned over and over in the literature. But then you start wondering, what does this pair of plus tell us? What it actually tells us is that if we only consider these particular words that are related to colors, and then look at the co-occurrence of these color names with either leaves or bananas, effectively, or statistically, leaves and bananas are extremely similar with each other. But we know that these colors should not matter when we determine the similarity between leaves and bananas. And what this tells us is that the statistical methods are picking up the signal that is spurious. In other words, this pattern or the association between the color names and leaves versus bananas exist, and then they are visible and they are apparent, but they are actually not valid. So this statistical pattern that is spurious is giving our statistical machinery a wrong idea of the meanings of these individual words, in particular, in this case, leaves and bananas. In other words, the statistical patterns that we observe in text reflect not only the true or intrinsic meaning of individual words or individual units or the composed, let's say, phrases, but also the statistical patterns reflect how those units are used in reality. That is the extrinsic use. And then there is the ambiguity between these two, and the statistical patterns don't really reveal between these two which one was the true cause that gave rise to this particular statistical pattern. So in other words, statistical patterns themselves cannot disambiguate the cause behind themselves. Let's look at yet another example that will look more alarming than the previous very innocent example of confusing leaves and bananas. So on the left side of this plot, we see the two clip arts images of doctor, medical doctor in particular. On the right side, we see again two clip arts that correspond to nurses. And regardless of the gender of an individual, we know that what their job is. In other words, neither doctor nor nurse is defined by the gender of a person who has that job. Very obvious, I know. You might think that why the hell is Professor Joe talking about this obvious fact? Everyone knows that doctor is a person who tends to a patient, and nurse is a person who also tends to a patient. And then there's nothing about the gender of those people that define what their occupation should be. Unfortunately, when we try to look at the same Google Books Ngram, what we observe is that the large amount of text that Google Books has, in fact, tells us a different story. With the word doctor, he co-occurs much more frequently than she does. When we think about the word nurse, the situation is opposite. In other words, the statistical patterns that we see in terms of the co-occurrence between a gendered pronoun versus either doctor or nurse reflects not the true nature or the true intrinsic meaning of the word doctor or nurse, but how these occupations show or manifest themselves in this society. And then it actually reflects the undesirable bias within the society beyond the word's true meanings. In other words, using the methods that we have talked about, we are going to indeed extract automatically a lot of aspects of the meaning behind many different individual words as well as any phrases that you can imagine. However, what is captured, that meaning that is being captured by these statistical methods will consist of both the intrinsic meaning of those words, but also how these words are used in the society, thereby encoding the societal biases as well. So unfortunate thing is that as I said earlier, and then let me emphasize here, statistical patterns alone simply cannot distinguish intrinsic meaning and extrinsic use of any individual linguistic unit that we are interested in. So we cannot really rely solely on this statistical paradigm in order to build our truly language understanding artificial intelligence agents. Instead, we must go beyond this statistical paradigm. Now, beyond toward where? Unfortunately, I don't really have the answer. This is precisely what everyone in the research community of natural language processing and understanding is trying to figure out. And I am very optimistic that we'll be able to find the next paradigm that's going to allow us to go beyond these statistical patterns and be able to allow us to build a system that is able to truly distinguish between the intrinsic meaning of linguistic units and how these linguistic units are used in various and different contexts, societal contexts. And by doing so, we'll be able to build a machine that does not emphasize or amplify the existing undesirable societal biases, but can in fact help us correct various undesirable societal biases that we have even without realizing ourselves. And of course, ultimately, we'll be able to build a truly true language understanding machine that is able to share their experiences among themselves as well as with ourselves, the humans, in order to greatly expand the horizon of knowledge and intelligence beyond what has been and what is available for now. And then this concludes the lecture on natural language processing. And then, and I hope you enjoyed this whole lecture. It consists of the several parts, so it may feel daunting, but I tried to make it as slow as possible and then make it as fun as possible. I hope you enjoyed it as well. And if you have any questions, we are going to have a online but real-time QA session soon. And then during that QA session, you'll be able to ask me as well as any other teaching assistants the questions that you have, or I'll be happy to hear any feedback you have as well. Thank you very much.